Okay, so in this class we will see uh, the next realization technique, that is called the cascaded technique, cascaded realization structure. Okay. So in the previous class we have seen the direct form. So in the direct form it is of two types, direct form 1 and direct form 2. So in direct form 1 we have seen like whatever transfer function we are having h of z, we make it to two terms h1 of z multiplied by the h2 of z, and here this h1 is represented by the zeros first and the h2 are represented by the poles. So whatever poles are there into the transfer function, that will be represented by h2z, and h1z represents the zeros. So first we will be having the representation. So this will be your h1z, and the next will be your h2z. Here input will be there, so input will always be there in the terms of x of n, and output will be your y of n, or in terms of z transform we can call it x of z and y of z. Okay, and the intermediate stage after the first one, it will be represented by w of n, or we call it w of z. So from there we can see, if we want to find out the h1z, it will be output, that is wz, divided by input, that is x of z. Similarly, if we want to find out the h2 of z, that will be output, that is y of z, divided by input, that is input for the h2 of z is w of z, so it will be w of z. So by using h1 and h2, if we multiply these two, we can get h1 multiplication with, if we are multiply h1z into h2z, it will be wz divided by xz into yz divided by wz. So wz and wz will be cancel out, and we will get it uh, y of z divided by x of z, and this y of z divided by x of z is represented by h of z, that is the transfer function that we are going to realize. Okay, so here the same can be derived. Okay, so here in this representation, the first part h1z represents the zeros, and second part represents the pole. This is the direct form 1. This is direct form 1. Similarly, in direct form 2, the same way we will be representing the first term h1z, second term h2z, but this first term will be represented by the poles, and the second term will be represented by the zeros. Okay, so in this case, if we are going to see, this is h1z, this is h2z, and here input x, and this will be the representation. This will be representing your poles, and this will be representing your zeros. So this is how the same process we can follow. The advantage in the case of direct form 2 is, so what is the advantage? It will be requiring less number of memory elements. So memory elements means the delay element that we use is considered to be as the memory element. So this delay can be represented in the form of memory. Okay, so in direct form 2 we are sharing the delay elements, so it is just reducing the memory requirement. So here the number of memory elements required is considered to be the maximum of m or n. So what is the maximum value of m and n? That will be the number of memory elements required. So m and n are the order of numerator and order of denominator. Okay, so whatever transfer function is there, so what will be the or we can call it the number of poles and number of zeros. These are all. This can be interchangeable. Okay, so out of these, if the number of poles are higher, whatever value out of this is higher, that will be the maximum number of elements required. Okay, but in direct form 1, if we consider the direct form 1, here the number of memory elements required are m plus n plus 1. Okay, but in case of uh, direct form 2, it will be the same, that is a maximum of these two. And also the multiplications and the additions are adder and multipliers. So we have seen the number of adders and multipliers required in the direct form 1 and direct form 2 will be the same. We call it m plus n plus 1. Okay, and also in case of uh, this one, direct form 2, the direct form 2, the same technique will be followed. That means we are going to uh, have the number of multipliers, the same number of multipliers will be required. Just a minute. Yes, so we were saying the number of memory elements and the multipliers in it. So whatever the complexity of circuit is there, that complexity depends on the hardwares, that one number of hardwares that is required to design that system. Okay. So in case of direct form 1, the number of memory elements will be higher because there is no sharing of memory elements, so it will be m plus n plus 1. Similarly, the multipliers requirement is m plus m n plus m plus 1. Okay, so this can be obtained by the expressions that we have got. The generalized expression for IIR system. Okay, from there, once we expand it, we can get it, or whatever structure we have designed or we are designing. From there also we can see the number of adders and multipliers. So the number of adders will be required are m plus n. So same number of adders and multipliers will be there in the case of that from 2 also. The only difference will be in terms of the number of memory elements. Okay. So same whatever direct from 1 and direct from 2 are having, same number of multipliers and adders will be required. The difference will be in terms of the memory elements. Okay. So this is the overview of the previous lecture. So in this class, we will see like how we can realize the IIR systems in cascade form. Okay. So here in cascade form, uh, any transfer function is given h of z. Okay. So here also we will be doing is we can convert this transfer function into h1 of z, h2 of z and so on up to hn of z, or any number of transfer functions. We can break this h of z such that all are, after multiplying all the different transfer function, we can get the h of z. Okay, so this first one is in cascade with second and third. So if it's the representation we need to form, then h of z will be considered as h1 in cascade with h2 in cascade with h3 and so on, at the last h of n. Okay, so this combined will be considered as your h of z. So this is how the cascade realization of IIR systems are done. The same is represented in terms of a mathematical expression. Okay, so here mathematical expression is like h of z can be having different transfer functions. So in that, different transfer functions h1, h2, h3 are there. So suppose h1, h2, h3 are in the numerator. It is break into two parts. One is only having the real parts, only the real you can say the solutions are there. Any transfer function that is h1z having real solutions, then it will be represented by this term. Okay, any transfer function that is having the equations, other solutions in the complex conjugate form, its solution is in complex form, then it will be of two types, like hk will be one pole and hk complex conjugate will be the second pole. Like the we call it like imaginary poles are always exist in pair. The same, if any pole represented by 2 plus j3. Okay, so if this is the pole, then another pole will be 2 minus j3. Okay, so the complex poles are always exist in pair. That's why it is written in two terms. So this is in case of zeros and similar in case of poles. Okay, so here k is ranging from 1 to m1, and here again k is ranging from 1 to m2. So the total number of m, so here m is for zeros, so m is for zeros. So the numerator represents the zeros and denominator represents the pole. It is represented by n. Okay, so here m will be equals to m1, k equals to 1 to m1. It is ranging, so m1 terms will be there plus 2 times m2, because m2 will be having two terms. One term is this one as separate transfer function, another one is second transfer function. So we can represent in terms of m is equals to m1 plus m2. Similarly, in case of n, the complete n will be n1 plus 2 times n2. Okay, so here g is a constant. So this is the generalized expression that a transfer function can be. Okay, so just it has break in this transfer function into different generalized representation. It is just for analysis purpose. Okay, once we will be doing the numerical problems, it will be clear to you. The same, once we have factored, okay, or this is in terms of the poles, or you can say solutions, whatever poles or zeros are there, in terms of that it is there, so we can separate it out and go for solving. Another one is if we have a factored product and that factor is having like if it is z plus 5. Okay, so if z plus 5 is there, that is okay, that will be considered once. If it is of the type z square plus 2 z plus 3, suppose this is the another factor. Okay, so if this is the factor, we will be making it in the form of 1 plus beta this one, and whatever this function will be there. Okay, we will go for designing this in the form of either direct form 1 or direct form 2. So if the transfer function is having a single first order system, this is the first order system, this is second order system, either we can write it 1 plus 5 z inverse, even we can write it this way also. Okay, so this way it is the same, this representation. The same This can be represented as 1 plus 2z inverse plus 3z minus 2. So this is how this representation is there. Okay. So a generalized transfer function can be having either this way or this way. Okay. So if the single first order system is there, we will be representing as a single transfer function, and if it is of second order system, we will be designing it in the form of direct form 1 or direct form 2 based on our choice. Okay, based on our choice, we will do then. This is just theory part. Okay. So the same representation there. So in the previous slide, we have seen. So two type of system. One is first order and one is second order. So mostly we will be preferring the direct form 2 structure to represent, because it will be requiring less number of hardwares or less number of memory elements. So we will be preparing to design the second order system in direct form 2 structure. Okay. So this is the realization, like if any first order system is there, only one daily elements will be required, then it will be represented like this. And if any second order system are there, then its realization will be in terms of this. Okay. So we will see the other terms into the example part. It will be clear. Okay. So just we will be going through some examples. So suppose a question is like, you need to obtain a cascade realization of the system characterized by the transfer function this. So this is the transfer function, and you need to realize it by using cascade realization. Okay. So here, first of all, to realize a system, we have to make in terms of negative power subject. Okay. We have to make uh, negative powers of z. Whatever z is written, we have to make it the negative powers. So first of all, we will see what is the highest power of z. So that is z is 1 z is here, 2, 3, and 4. So total, if we expand this, it will be total z to the power 4 term. So if z to the power 4 is there, so we have to write all the z terms in the negative form. So we will just multiply it by z to the power minus 4 on both the sides, or you can say on the numerator and denominator. After multiplying, we will see it is h of z is equals to 2 z to the power minus 3 into 1 plus 2 z inverse. The same, we will be multiplying and we will be getting the same similar function. Okay. After multiplying, what we need to do is, in case of cascade form, whatever h of z is there, we will be making as the multiplication of different transfer functions. Okay, like h1z, h2z, and h3z. So based on our requirement, we can make it different terms. Okay. So once we will be separating, so here 2z to the power minus 3, we are separating it out. Okay. Then this term is being combined with the first term. Okay. And all other terms are separated. So all other terms are separated is like this 2 is a constant, like a gain, that was g in the generalized structure in the previous slide. So this g is the gain. Okay. So the gain is there. 2 will be a constant, that is gain. And the first term, that is 2 dot something is there. So in one transfer function, like again with that another transfer function, the h the one z represented by z to the power minus 3. Similarly, h2, this transfer function is represented by h2. Similarly, this transfer function is represented by h3, and this transfer function is represented by h4. So we have just break the given transfer function into different transfer functions, and that will be the multiplication of different transfer functions that will be giving out the h of z. Okay. So once we have got the different transfer functions, we will be realizing this h1, h2, h3, h4 transfer functions with the technique that we have seen is direct from 1 or direct from 2. Either from direct from 1 or direct from 2, we can realize this. So to realize 2 will be multiplied with the whole system, so it will be just multiplication. Okay. Then h1z is z to the power minus 3. That means 3 delay elements are there, so 3 delay elements will be used. Okay, 1, 2, and 3. So this is the first one. So 2, this is the h1 of z. Then h2 of z. So h2 of z is having numerator and denominator. Okay, so it is having numerator and denominator. So the same technique, the direct form 1 or direct form 2. Basically, we will be following the direct form 2 structure to realize the h1z. And one more thing, like we should be making sure the transfer function we are generating the transfer function, all the numerator and denominator should be same. Then the order of the numerator and denominator should be same once we are going to realize the separate transfer function. This will be helpful to optimize the requirement of memory elements. Okay, so here z to the power minus 1 is there, here also the z to the power minus 1 is there. Okay, so both are having 1 z to the power, so that means only one delay will be required. Okay, so that value or that transfer function will be realized by using the direct form 2. So once we will be realizing this with the direct form 2, here the poles will be used. Poles realization will be there this way, and here zeros will be realized. So for realizing the poles, it is 1 minus is retained. So if it is already minus, then there will be no sign change. We will be writing 0.1. Okay, coefficient. And similarly in case of zeros, whatever delay element is there, after delay element we will be multiplying it with the two constant adder. Okay, so this is the realization of your h2 of z. Okay, similarly for h3 of z, so in h3 of z there is no zeros is not there, only poles are there. So poles are on the, you can say, in direct form 2 structure, the poles are represented on the left part of the delay element. So one delay will be there, and here it will be a multiplier. So the coefficient of the multiplier will be here 1 plus is there, as if it is minus, then the same sign will be there, but it is plus, that means its opposite sign will be here. So to make it minus, we will be writing it like the same. It can be represented in terms of generalized expression 1 minus 0.5 z inverse. That will be like this. So now it is of the form, so whatever sign is there, that is minus 0.5, so minus 0.5 will be the coefficient here. Okay, similarly the next one, the next term is 1 upon 1 plus 0.4 z inverse. So here again it is only the poles are there, no zeros are there. Here 1 plus is there, so it will be represented by 1 minus 0.4 z inverse. So here the coefficient will be minus 0.4. So again the minus 0.4 coefficient will be used. Okay, so this is for h3 of z, sorry, h3 of z, and this is for h4 of z. Okay, so this is how the cascade structure will be realized. Okay, is there any doubt, or you can ask? So this is the cascade realization. The next realization technique is the parallel realization. So as we have seen the cascade one, so for cascade, whatever transfer function we are having, that will be represented in terms of multiplication of different transfer functions. Similarly, in case of parallel realization, we should be writing h of z such that it will be having the addition of different transfer functions. Okay, so instead of multiplication, this h of z will be represented in terms of different summations of different transfer functions. Okay, so to make this summation terms, what we will be doing is we will be making the partial fraction. So whatever transfer function is given, we will make the partial fraction method to represent this type of systems. So this is the generalized structure of transfer function to realize that transfer function in terms of parallel realization. Okay, so here a single term is there. If z to the power 1 is their coefficient, the coefficient of z is 1. Okay, one power system will be there, or first order system will be there, then this will be the term. This will be how the representation will be there. If it is a second order system, that means the second order system means that their poles will be lying into the complex conjugate form. So it will be of the form 1 minus dk z to the power minus 1 into 1 minus dk star represents the complex conjugate and z to the power minus 1. So these two will be of two poles will be there in the complex conjugate nature. So these are complex conjugate poles. Okay, and in the above side, like the partial fraction method, similarly we do once only the single term is there, a constant is there. If two powers of z will be there, uh, coefficient will be of the form of a and z inverse minus b. It means there will be two coefficients required to represent the partial fraction. And similarly, a constant is there. That means only the zeros are there. Then this term of representation will be there. Okay, so this is the generalized structure. Okay, once we will be following the questions, it will be more clear. And also here it is assuming like we are having a single pole system, or only we can say the pole system are there. If only poles are there, then this will be the representation. Okay. So if this is the representation of a parallel realization, then this will be represented by one input will be there. Then this input will be going to two different transfer functions, that is h1 of z and plus h2 of z is there. So plus sign will be giving you out the parallel realization. And after parallel realization, it will be giving you out by an adder, and then this will be your output, that is y of z, and here it will be x of z, or we call it in terms of time domain, it is x of n, and here y of n will be the output. And this block will be giving you out the h of z. So y of z is output, x of z is as input. Okay, so from there we can call it h of z is equals to y of z divided by x of z. Okay, so similarly in parallel realization, the transfer functions should be represented in terms of addition of different transfer functions, and then individual transfer function will be uh, represented or realized by using direct form 1 or direct form 2, and from there it can be represented in terms of parallel realization. So this is how the parallel realization will be taking place. Okay, so once we have seen the generalized expression, these generalized expressions can be represented like that. Okay, and this is how the relation will be there. So if a constant is there, uh, this is the all pole system. Here a single constant is there. Okay, so this constant will be directly having uh, a relation between x of n input to output with the constant multiplier. Okay, this is the constant. For other terms, okay, so for other terms, this is the term. Okay, so this is the second order system. The second order system means two delay elements will be required. So two delay elements will be there. Okay, on the pole side, because on the pole side This is denominator. So on the pole side, two elements will be there. On the zeroth side, only one delay element is required. So here, after one delay, a feedback will be there. Then there will be nothing. Okay. So the same, the first term, another one is the second term, similar to this, third term, and so on. So any system is there. If we are going to represent in terms of parallel, this will be the structure, generalized structure. Okay. So now we will see some questions based on that. Suppose the question is determine the parallel relation of IIR filters having transfer functions. First one is h of z, this one, and second one is another transfer function, that is this one. So we will proceed one by one. Okay. So in order to find the parallel relation, the partial fraction expansion should be done. Okay. So to do the partial fraction expansion, what we do h of z divided by z. Okay. So first of all, we will be finding this one, h of z divided by z. Okay. So once we will be proceeding with the analysis, we will find out h of z divided by z first. Okay. So in the first case, h of z divided by z, that will be giving you out 3 by 2. Here also the coefficients of z are the, you can say, the whatever z is there, whatever coefficients are there into the z, we will be making sure in the separate, if it is a first order, like this is the first order, this is the separate first order, this is second order. So not in the second order, but in the first order, the coefficient should be a 1. Okay. So here 2z plus 1 is written. So always the terms will be in the form of z plus something. Okay. So z plus k or z plus whatever constant is there. So to make sure this, we will be taking 2 outside, and this 2 is divided. Okay. So after simplification, this will be the representation. Okay. So h of z divided by z will be equals to this. And now this is one term, this is another term, and this is the third term. So we will be making the partial fraction by using this. So z will be another one, first one, second one is z plus 1 by 2, third one is z plus 2. So it is of the first order system, z1 and z plus 1 by 2. These are first order systems. So in partial fraction, it will be a1 plus this one plus a2 divided by this, a3 divided by this. Okay. So this is how the partial fraction we should be proceeding with. And now we have to find out the a1, a2, and a3. Okay. So the same. So once we are going to find out this, what we do is, whatever this is the term, okay, this term, the complete f of z is there. If we are going to find out a1, we will be multiplying this denominator part of a1 coefficient, this one, z will be multiplied by fz. Okay. And then we will be putting z equals to 0. We will be putting this z is equals to 0 into this after multiplication, and whatever value will be there, that will be coming out to be a1. Similarly, to find out the a2, the same, whatever the denominator part is there into the a2, the same will be multiplied by the f of z. And after multiplying this f of z, we will be making sure like z plus 1 by 2 is equals to 0, or we call it z is equals to minus 1 by 2. So we will be putting z equals to minus 1 by 2 after multiplying this term to fz. And then putting the value, we will get the value, that constant will be your a2. Similarly, a3, this is the denominator part. So this denominator part will be multiplied by f of z. And after multiplying this f of z, we will be putting z plus 2 is equals to 0. And from there, we can get z is equals to minus 2. So z is equals to minus 2 will be putting the value. After getting the value, after multiplying these two. Okay. So this a3 value will be 1. So once we have got the a1, a2, a3 value, we will get h of z divided by z is equals to 6 by z after putting the coefficients value, and then I will just find out h of z, and thus h of z will be multiplication. We will be multiplying it, so it will be 6. Z will be multiplied. So this one. Okay. So this is the first one. This is the second transfer function. This is the third transfer function. Okay. So we will proceed with the designing or the realization. We will be realizing this in terms of hardware. So each term will be realized in terms of direct form 1 or direct form 2. We can use any of the two methods. So basically we will be following the direct form 2 only. Okay, the same, because it requires less number of memory elements. So x n will be there on the input side, output side y of n. So there will be a direct, because this is a constant term, so there is a direct path between xn and y of n. So it will be having a constant multiplier 6. Okay. The second term we will be realizing this is 4. Okay. So this is 4 divided by 1 plus 1 by 2 z inverse. So while realizing, the transfer function should be in terms of z to the power minus 1, because after while doing the partial fraction we will be taking the positive coefficients or positive order of z terms. But in case of realizing the transfer function by using direct form structure, the transfer function should be written in terms of, or you can say should be in the function of z to the power minus 1 or negative powers of z. Okay, so this type of function should be there. So we will be making this type of function, and then we will be realizing by the direct form 2 structure that we have already seen into the previous class. So 6 will be here, that will be a constant term. So the second term here 4 is a constant, so 4 multiplication will be here. And another, this term is on the denominator side, poles are there, so poles will be here. So one delay element will be required, and the coefficients here 1 plus is there. So its standard form, it will be written like 1 by 1 minus 1 by 2 z inverse. Okay, so here coefficient will be minus 1 by 2, so here minus 1 by 2 will be there. This will be the realization of this term, so this will be in parallel with 6. So this will be having in parallel with all these two terms, so it will be in parallel with the 1 will be a constant. Okay, and this 1 plus is there, so it will be realized like 1 minus 2 z inverse will be there. So here minus 2 coefficient will be used after one delay element. So this is how the realization in parallel form will be taking place. If you have, you can ask. Okay. The second question, one more question is there. H of z, that is given to be 3z 5z minus 2. Okay, so this is the question. So to make the partial fraction, we will be considering fz is equals to another function h is equal to h of z divided by z. So h of z divided by z will be uh, making sure like if from there this z is coming out here, or if there is no z, we will be just dividing the complete h of z on the numerator and denominator side by the z. Okay, so this z will be coming out here, so this z and z will cut it out, and it will be remaining 5z minus 2 divided by z plus 1 by 2 z minus 1 by 2. So here two terms are there, the first term and the second term. So with respect to first and second terms, partial fraction will be there. So with respect to first one, if it is a1 is the coefficient, with respect to second term, it is a2 is the coefficient. We will be finding the a1 and a2. After finding the a1 and a2, we will get the h of z is equals to 27 by 5 z by z plus 1 by 2 minus 2 by 5 z in divided by z minus 1 by 3. So to realize this, what we need to do is the z to the power minus the z power will be in the negative form. So we will be realizing it by doing the dividing this term, whole term h of z by z on numerator and denominator both. So once we will be dividing, it will be giving out this one. So this is the first term, this is the second term. Okay, so here h1 of z, here h2 of z, and this is plus. So here plus is there, this coefficient will be terms in multiplied by minus 2 by 5, that will be representing the negative coefficients. Okay, so once we are going to realize, the first term will be here. So in the first term it is 27 by 5, it is constant multiplied. So either we can multiply it here or we can multiply it here also. Okay, so any of these two methods can be used. So here the first term is there, so 27 by 5 will be multiplied. The second is only all pole system is there, so it will be positive is there, that means its coefficient will be negative, so negative 1 by 2 will be there. The same in the second side, it is minus 2 by 5, so minus 2 by 5 will be the coefficients. And then it is 1 minus 1 by 3, so it is already minus, so there will be a positive coefficient. Okay, so this is how the realization of parallel form should be done. Okay, so up to here, if anyone is having any doubt, you can ask.